Welcome to the first video for our 6th class time section of videos. Today we're going to be talking about conformations of organic molecules. I've chosen to start this video with a demonstration using a molecular model of ethane. So you can see the black polyhedra represent carbon. There's a carbon-carbon bond in white, and we have a carbon-hydrogen bond in pink, and then the white spheres represent hydrogen atoms. And so ethane is a very simple organic molecule. You can also get a molecular modeling set that might help you along with this section on conformations, as well as future chapters such as stereochemistry and just building molecular models in general. You can find these HGS molecular structure kits online fairly cheaply. I believe there's a reference in the syllabus to them. At any rate, we're looking at ethane, and we're going to cite down the carbon-carbon bond, and there are a couple of different conformations we could talk about with respect to ethane. So in one conformation, you can clearly see that the hydrogens on the carbon in the back are staggered in between the hydrogen bonds for the carbon in front. Now we know that we can rotate freely around a carbon-carbon single bond, and so if we start rotating, we can see that eventually we get to a conformation in which those hydrogen atoms are now eclipsing each other. So by eclipsing, they are directly in front of each other. Typically we represent an eclipsed conformation as slightly twisted when we draw something called a Newman projection that we'll talk about here shortly, but I figured I would show you what these two different conformations look like with an actual model before we look at them as they are represented on paper. So staggered and then eclipsed. Alright, so let's look at them on paper. So, conformations of organic molecules. Here I've drawn out a staggered conformation for ethane. You can see there's the straight lines are in the plane of the page. The wedged bonds are supposed to be coming up out of the plane of the page, and the dashed bonds are going back behind the plane of the page. One could imagine how this hydrogen would be staggered between these two if you were citing down this carbon-carbon bond. Of course, we could turn this front carbon such that this wedged hydrogen is now in the plane, and this would get us to the eclipsed form because the wedged hydrogens are now eclipsing each other, as well as these hydrogens that are in the plane, as well as the set of hydrogens that have the dash bonds if you're citing down the carbon-carbon bond. So, as we said, there are two different conformers or rotamers of ethane that are shown above. And this leads us to the question of what is a Newman projection? Well, let's consider a bond line diagram of staggered ethane. What would the floating eye in the plane of the page see? Well, if it's an eye attached to a body in the plane of the page, and it's looking down this carbon-carbon bond, it would see the front carbon, and I've drawn that as a point now, and this hydrogen atom that possesses a wedged bond, I've labeled HA, the eye would see HA going up and to the left, its left. This hydrogen that's in the plane of the page drops straight down from that carbon that the eye first sees. And of course, this hydrogen that's got the dash bond goes up and to the right, according to the eye's perspective. Now, the eye cannot see the carbon that's directly behind the carbon that it's viewing. So what we do is we draw this obscuring circle behind these carbon-hydrogen bonds, but it can see the atoms that are coming off of this carbon that's behind the carbon atom in front. And so this hydrogen that's drawn in the plane of the page, I've labeled HB, it will be staggered between HA and then the hydrogen that goes up and to the right on the front carbon. Similarly, these hydrogens that get the wedge bond and the dash bond also appear staggered between these front hydrogens. So that is a Newman projection for ethane. Staggered ethane. So we just saw that Newman projection for staggered ethane. What about the eclipsed form? Well, in the eclipsed form, the hydrogens in theory are right behind each other. We typically draw eclipsed forms where these groups are just slightly at an angle to each other, so we can see what the group is that is being eclipsed by the front atom bonded to the carbon. So this is our Newman projection of an eclipsed form. So you should be comfortable to sight down a given bond in a bond line structure and make a Newman projection. Similarly, you should be able to draw a bond line structure from a Newman projection. And of course, we'll get practice doing this during the class time and in practice problems as we prepare for our exams. So the last idea for this particular class time has to do with what an energy versus rotation diagram would look like for the process of staggered ethane converting to the eclipsed form. Because if you're a carbon-carbon single bond and you're not constrained in a ring, you can freely rotate. So what does that process look like? Well, we might start off at 0 degrees with this staggered conformation, and HA is pointing straight down. I'm going to hold the back carbon in position, and I'm going to start rotating the front like a propeller. As the front rotates to the right, we get an angle of about 60 degrees when we reach an eclipsed conformation. And this eclipsed conformation is higher in energy than the staggered conformation. Of course, if we rotate the front carbon another 60 degrees, so we get a net 120 degree rotation from our 0 degree starting point. Now HA goes up and to the right, and we've reached another staggered conformation. You'll notice that this staggered conformation is energetically equivalent to the 0 degree staggered conformation that we started at. Again, if we hold the back carbon constant and start rotating the front carbon another 60 degrees to get to 180 degrees, we get another eclipsed conformation. And of course, this eclipsed conformation is identical in energy to the eclipsed conformation we observed at 60 degrees. And we can continue through this process, rotating another 60 degrees to 240 degrees with a staggered conformation, and 300 degrees is going to be an eclipsed conformation. And finally, 360 degrees would be the original conformation that we started out at 0 degrees at. Now, you could say, Dr. Wagner, this is interesting. Once your molecule starts rotating, does it keep rotating in just a single direction? And the answer is no. We might rotate this far and then go back this far and then rotate this far again. maybe start going backwards. These molecules can rotate in either direction, and they can switch and go back. And there's actually interesting research where chemists are trying to create molecular ratchets that can only rotate in one direction. That would be kind of an interesting advance to being able to make molecular sized machines with function that could be useful. So the change in energy for this process is about 2.9 kcals per mole. Why is the staggered form higher in energy than why is the eclipsed form higher in energy than the staggered form? And there are a few answers. The primary one is repulsion between the hydrogen atoms bonding electrons. So they feel each other's presence. We call that sterics. And there's another effect that's going on in this, but we will start our next video in the series discussing that particular effect.